Hello, everybody, and welcome to the Cosmos Show, a place to be if you're curious about the universe. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here you can pick the brains of astrophysicists, get advice from a space doctor, learn about what's going on above your head, and find out what astronomers have to say about life, all in the same place. Join us every other Tuesday, 6 p.m. Mountain Time, live on YouTube, Twitch, and now Facebook as well. You can chat your questions on Twitch and YouTube. You can also call in live and ask us questions, make comments by using the Zoom login info on your screen. We'd love to hear from you, so give us a ring. On this week's show, we are going to chat with Dr. Asante Correa, the professor of physics and astronomy at the University of California, Irvine. He studies cosmology, which is the origin, evolution, and fate of the universe. Tonight, he'll share some thoughts about some of the telescopes that will come after the James Webb Space Telescope. Now that James Webb is out there, we're already talking about what's going to come 20 years after we get all that great stuff from James Webb. But specifically, the answers that these telescopes will answer about the very early universe. But before he joins us, let's welcome our co-stars. First, postdoctoral scholar from the Simons Observatory, it's Dr. Nick Galitsky.
Hi, everybody.
Hey, Nick. Next, PhD candidate in astrophysics from the University of Chicago and host of her own YouTube show, Nora's Guide to the Galaxy. It's Nora Bailey.
Hey, everyone.
Hey, Nora. And last but certainly not least, Deputy Director of Education and Public Outreach at the Vera Rubin Observatory. It's Dr. Lauren Corlies.
Hi, happy to be here.
Thanks for being here, Lauren. And unfortunately, Dr. Danny can't make it today, but she will be back in a couple weeks. So let's get started with Astro Advice, life advice from astronomers. And our quotation this evening is from Stephanie Kwolek, and she was an American chemist who worked for DuPont for about 40 years, most well known for discovering the first of a family of synthetic fibers of exceptional strength and stiffness. I'm going to try to say this chemical formula here. Polyparaphenylene terephthalamide, more commonly known as Kevlar. So she's the inventor of Kevlar. And what she has for us is this. All sorts of things can happen when you're open to new ideas and playing around with things. So I'll turn that over to the co-stars and see what they have to say about that.
I like this quote. It's sort of... Oh, go ahead, Nick. No, you first.
I was just going to say, speaks to the experimental side of things. Yeah, a lot of things happen aloud when you're just messing around with things. Usually you break stuff, but sometimes it works. And sometimes you find something you definitely weren't expecting to.
What's the ratio there, Nick, of breaking things and figuring out new things?
Breaking things versus serendipitous discoveries tend to be a little lopsided.
Yeah, I was gonna say, I feel like this quote comes closest to like how I feel like best as a scientist, where you're just playing around. Like, oh, well, what if we tried this? What if we thought about this? And we could try this crazy thing. And why I got into the computer stuff, because you can just be like, oh, well, if I tweak this thing and see what happens to my galaxy and tweak this thing, and just always, I don't know, seeing how you could break things even in computers too, not just with hardware.
Nice.
Yeah, I like that too with my simulations. It's like, I'll just do something and see what happens. But I think it's also, I think it's really hard. It's very easy to say that you're open to new ideas, but when you're doing science, I think the new ideas are the hardest because you're you have to fight a battle uphill to get them accepted. And it's not like, there's not an answer key. There's no one to tell you like, yeah, you got it right or whatever. So when you're like really going down a new path, I think it's really kind of scary. And yeah, so I think that's where kind of the magic happens, but it's also very intimidating at times.
Special note, I should say thanks to Stephanie for the Kevlar, because we actually use it in cryogenics. A very strong material with low thermal conductivity. It's comes in handy.
Oh, cool. Say more about that.
It's the hard way to suspend things. So in cryogenics, it's all about keeping things cold. That means isolating them from their environment. And so we look for mechanical supports that are strong, but don't conduct heat well. And Kevlar does that, but it's a string. So you got to suspend your basically your, sometimes like telescope focal planes or that sort of thing via a series of Kevlar strings that are tensioned just right. Anyway, can be done. It's tricky. But it's really effective. There's very little thermal conductivity through Kevlar. Fun fact.
That's really interesting. So I remember back in the day when I was an undergrad, I had this summer internship, research RU type deal, and I was in the lab, and some PhD student was working on this detector, and he had this detector suspended by these little strings, and I bet that was Kevlar. Very cool. That connects the dots for me there. Thank you, Nick.
It sounds a bit nerve-wracking though. Like, what's the biggest thing you can suspend with Kevlar? Like, oh, please stay.
Yeah, it gets even trickier because Kevlar has an inverse thermal expansion. So as it gets colder, it'll expand. So you have to have all these like spring tensioning it. But if you overdo the tensioning, it'll break. And then, so that's why most people don't use that. Yeah. If you do, anyway.
Have to be brave, huh?
I know the mirrors on the LIGO interferometer are suspended somehow. Is that Kevlar as well, or is that something else?
No, I think they do even crazier stuff. It's like threads of glass or something horrifying. Huh. Not that I know intricate details, but I remember looking it up, and it's like one time the engineer accidentally brushed against one of these members and it just poof into thin air. So they might use it in part of it because it's like this multi-stage pendulum isolation thing. LIGO's an insane engineering challenge once you start digging into it. I do not know all the parts, so it wouldn't necessarily surprise me, but I think that particular element has something even crazier. Yeah,
I have been deeply fascinated by the intricacies of LIGO. It's yeah, pretty awesome. Any other?
Oh, just saying on that, yeah, that's all sorts of things can happen when you're playing with new ideas, including discovering gravitational waves.
Yeah, right, there you go. I assume you've heard the story of how they turned the detectors on for like the first major test and detected a perfect signal within the first couple days.
So lucky. I could go for some of that.
Right. Well, apparently they spent like the next month trying to debunk it because they didn't even believe it because it was such a perfect signal right off the bat.
Yeah, you haven't even fully commissioned everything like you would be. Was it working? Was it not working? We're not sure. So yeah.
Right. And apparently they went as far as looking for devices that people might have hid to sabotage to create that signal. It was so out of the ordinary. Any other thoughts on this piece of Astro Advice? All right, well, let's move along down to Astro 365, this day in astrophysics history. And so today,
I think we got a comment from the audience.
Oh, we did. All right.
Going back to the Kevlar.
Oh yeah. So Tom Hertwig says he thinks Kevlar is used in I just lost the chat. Used in industrial fire risk areas, implying a benefit of low thermal conductivity? Question mark.
Yeah, that would make sense. I mean, like Nick was saying, if you're trying to keep something cold, then you want it to be thermally isolated. But on the flip side, if you're trying to keep something hot from spreading that heat, then it would also be beneficial to have something with low conductivity.
As long as it's also not flammable.
That's true. I don't think Kevlar is flammable, is it?
I don't know. We got a spool of it in the lab. I'll try next time.
Or inflammable. Very confusing pair of English words there.
Yeah, I don't know.
I guess I'm thinking now, like, could you make like a fire hose out of Kevlar? Or do they make fire hoses out of Kevlar? I'm not sure. The material they make it out of
is already doing a good job for cooling it.
Very thick. But you can also make body armor out of Kevlar, but
Very nice.
That's slightly outside of these scientific applications.
An interesting application, though, nonetheless. Thanks for that, Tom. Appreciate your chiming in there. So getting back to Astro 365, today in 1783, William Herschel discovered the point in the sky towards which our solar system is moving. And there happens to be a star close to that point. So it's called the apex star in the constellation Hercules, Lambda, that star. Turns out that Herschel was roughly 7 or 8 degrees off, but not so bad for 1783. And interesting side note that I did not know about William Herschel, turns out that he was Jewish. I just had no idea that he was. And so, yeah, found that out when I was looking up this tidbit, and yeah, thought that was an interesting piece of info. I looked at everything that happened within about 2 weeks of this date, and unfortunately, there's a lot of morbid stuff as we got to last time, and so I took all that out. So we're not going to talk about all the morbid moments in astrophysics history that we did last time. However, there is one thing we do have to talk about, which has to do with an astronomical event that's coming up in just 2 days, on February 3rd, which is Groundhog's Day. And so some of you may already know that the Groundhog's Day is actually one of these astronomical holidays that we call cross-quarter days. They're the days that actually fall roughly halfway between the solstices and the equinoxes. And so on February 3rd, that puts us about halfway between the winter solstice, which is already passed, and the spring equinox, which is yet to come. So we're halfway there. And our director of operations did a little homework on this, and she also found out today that it turns out that winter is actually the shortest season by about 1.1 days. And so it's less than half, and it's the shortest less than half season that we have to go through. So we're getting there, folks. We're almost there. These cross-quarter days were celebrated by lots of ancient people, including the ancient Celtic people. And so we actually celebrate 3 of the 4 cross-quarter days throughout the year. We just don't typically talk about it as such. The other one that most people will know about is Halloween, the cross-quarter day between the fall equinox and the winter solstice. And then everybody probably knows May Day. But the fourth one is a bit more obscure, and it's not really celebrated anymore. It's called Lammas Day. But we don't really do much with Lammas Day. Maybe in some parts of the world they do, but not here in the States. So anyways, these cross-quarter days, in my opinion, and I'll defer to the co-stars on what they think about this. I think the cross-quarter days should actually be used to mark the beginnings and the endings of the seasons, whereas the solstices and the equinoxes are actually the halfway points, right? Because that's like longest day of the year, shortest day of the year on the solstices, whereas the cross-quarter days really bring in the beginning of the seasons. So I had my way with the calendar, that's what I would do. But curious to hear what the co-stars think
Wait,
about
so
that.
you think that it should be spring now?
Yeah, technically this should be the first day of spring, and like the spring solstice, that's actually midpoint.
I'm not sure. I'm not sure I'm with you on this one.
No? What
Not
about
feeling
the
like you're out
solstice?
of winter, huh?
What about the
not even close?
But I mean, but think of like, so the winter solstice, right? That's definitely the midpoint of winter. So if that's the midpoint of winter, where does it begin? I know there's like a seasonal lag.
I think that makes sense as the beginning of winter, because there's lag, right, with the climate. So like,
Right.
so the actual coldest point is about a month after the winter solstice. So it does make sense to me.
Well,
If anything, I think if anything, you could maybe argue, you know, a couple weeks before. I know, so my partner is from Australia, and they do not use the solstices and equinoxes. Equinox. I don't know. Anyways, they just use the
I
first
like
of that
equinox.
month.
Let's
So
go with that.
he is always telling me that winter, or you know, for them summer should start on December 1st. And I could buy that, but I think that pushing it all the way back to Halloween is a little much, in my opinion. But
That's fair. That's fair. No, I'm just bringing this up for the sake of argument. I thought it would be provocative. I mean, I guess my claim is that temperature shouldn't have anything to do with the seasons. It should be strictly astronomically speaking, right? Like why should it be temperature? I think it should be like where the Earth actually is relative to its orbit around the sun.
I mean, I could see that, because obviously your temperature is going to depend very heavily on your local latitude. For example, in Chicago, winter is about 6 damn months of the year. But
Yeah.
I think there's still a local minima and maxima, and the seasons in my mind are tied with climate. And so I do think that it's less of an astronomical phenomena to me and more of it's climate phenomena. But
Okay, fair enough. Nick, Lauren, what do you think? I'm okay if I'm outnumbered here. Let's just get it out.
It's American, so we better tie it to the commercial sector, right? So Thanksgiving, clearly a fall holiday. You can't, so maybe right after that, when you start playing Christmas songs in the stores, all right, and then you got to decide, well, is Valentine's Day a spring or a winter holiday? And then are we on to St. Patrick's Day as your dividing point? I don't know.
So I get it. Like forget climate, forget weather, forget astronomical events. We're just going with Hallmark.
Exactly. The Hallmark seasons.
What about the fiscal year?
Oh, so confusing because they start at different times depending on where you are.
Yeah.
The government fiscal year always was so confusing because it's like one quarter shifted from the calendar year. It's like, why?
Doesn't make any sense. I think they just do that to confuse us.
I think so too.
So do you do your taxes in spring or in winter?
Because my birthday is early September, and it is technically a summer birthday, but I will say that most people do not agree with me when I say that I have a summer birthday.
Yeah, I mean, it's funny, like when you just like say September, I definitely think of fall.
I kind of do too. But fall starts in September. It just starts,
Sure.
A few weeks into September.
And if you went along with my reasoning, it would totally be in fall, and then you'd be all set.
No, I want to have a summer.
I mean, oh no, sorry. No, if you went along with my reasoning, it would totally be in summer, and then it would be fine.
Okay.
Anyways, I thought that would be fun. So I still say that solstice season equinoxes should be the beginnings of the season. And I also have a buddy who is pretty convinced that we should have 13 months each calendar year, because we actually really do have you could split up with 13 lunar cycles, and it would work out pretty well. So anyways, that's a conversation for another day. Speaking of days, some other interesting events in the first couple weeks of astrophysics history in February. On February 2nd, 8 of the 9 planets aligned for the first time in 400 years. And that
8 of the 8 planets?
Well, this was in 1962, so Pluto was still a planet then. So it was 8 of the 9
Pluto
planets.
one of the ones that aligned?
I don't know if it was one of the ones that aligned. It may have been the one that didn't. I didn't actually look that up. That would be interesting. But anyways, that was 1962 that happened. Clyde Tombaugh was born on February 4th. Speaking of
Pluto.
Clyde was probably rolling over in his grave when in 2006, the International Astronomical Union decided Pluto was not a planet. Thank you, Mike Brown and cohort. But yeah, Clyde Tombaugh was born in 1906, and talk about toiling away on tasks. He was just using photographic plates, blinking light between one and the other, trying to find discrepancies from one picture to the other. And lo and behold, he saw a little moving dot. And it turned out to be a planet that we now call Pluto, in the subcategory now of dwarf planets. But it will still be a planet to so many people, no matter what the International Astronomical Union says. That's probably the most frequent question I get asked on all the stargazing programs that I do. What do I think about Pluto, and do I believe in aliens? And I tell them Pluto is definitely not a planet, and life most certainly exists off the Earth somewhere. And maybe James Webb will help answer that question once and for all. Let's see. Nicholas Copernicus observed the moon eclipsing the star Aldebaran in 1497. Kind of interesting. Edmund Halley was appointed the second astronomer royal in England in 1720. That was on February 10th. Nicholas Copernicus did that observation on the 9th of February. And then on February 13th, Italian astronomer Galileo Galilei arrived in Rome for trial before the Inquisition for professing his belief that the Earth orbited around the sun. And that was in 1633. Thank you, Mr. Galileo. But getting back to Groundhog's Day, there was a death in the meteorological family that we did want to make note of. And that was one of the lovely groundhogs that is brought out on each Groundhog Day to observe his shadow, which legend has it actually foretells whether or not we will have an early spring or not. If the groundhog doesn't see his shadow, it's an early spring. If he does see a shadow, then more weeks of winter. But at least in New Jersey, that will not be happening because they couldn't find a replacement. So Dr. Danny, that little bit of morbidity is for you. Sorry that you couldn't join us tonight, but throw that in there just for you. Co-stars, any other dates that you noticed that perked your fancy on the calendar for these weeks of February, or any other comments related to the stuff that I brought up?
Yeah, I think, if we're talking history, it's February 1st. It's the first day of Black History Month. So I encourage everyone to go out and find out about one Black astronomer they didn't know about before, because there are lots of them.
And Nora Bailey actually has an incredible show about that on her YouTube station. So you should definitely go to Nora's Guide to the Galaxy and type in a search for Black History Month. That was actually one of the first shows I watched on Nora's channel, and it is excellent.
Thank you.
Yeah, and thank you for mentioning that. I saw that on my calendar today, and I meant to bring it up, and I forgot, so thank you.
Yep.
Any other comments, questions, concerns, compliments? All right, well, it is time for us to take a short break, and we will be back in just a moment with our special guest, Dr. Asante Correa. So stick around, and we'll see you back in a couple minutes. All right, welcome back, everybody. We're here with our special guest, Dr. Asante Correa from the University of California, Irvine. Thanks so much for being here tonight.
Oh, thank you for having me. It's great to join you guys, talk about some stuff.
The pleasure's ours. We'd like to start off the guest spot with the same question each time, which is, what's the one question that you wish everybody asks you, but nobody ever does?
Ooh, I don't know about everybody asking, but I'll stay on topic and I don't want to give away. I was watching this movie over the weekend. I wish somebody one day would ask me, if I want to go on a road trip around the galaxy.
Nice.
Maybe it won't be a road trip, but I guess it's a star hop around the galaxy. But yeah.
All I can say to that is make it so.
Yep. Let's hope.
Nice. I like it. We I'm blanking on his name right now. We had Miguel Alcubierre on the show a few months back, and he was telling us about his design of the warp drive. So
nice.
Maybe we can make that happen for you at some point.
Yeah. Maybe somebody will, with lots of money will invest.
That's all we need, right? Maybe we can talk to Elon about that after he lands on Mars.
Yeah, something like that.
Yeah, there we go. Asante, tell us a little about how you got into astronomy and what area of astronomy you study in cosmology.
So I guess back when I was, back a long time ago, this was back in Sri Lanka, where I grew up. I used to have in my, I don't know, early teens or whatever, even before that. Anyway, I used to have I don't think this company exists anymore. A camera, and I used to do pretty awful astrophotography with the film. Very expensive, by the way. Nowadays, we take I don't know, 1,000, frames. But back then, a one photo would cost you so much money, kind of when you're a kid, especially. But yeah, so the company was Konica. I think they don't exist, I think, anymore. But anyway, so want to do some astronomy interest. Then I came to US. I went to MIT undergrad doing research. There was Jim Elliott. I don't know if you guys know the name or heard the name. He discovered many things. He discovered the rings around some of these gas giant planets using stellar occultations. He flew there used to be a airplane. And nowadays there's Sophia, but back then it's called Kuiper Airborne Observatory. It's a small plane with a small telescope. So yeah, as an undergrad, I flew on that one with Jim Elliott once. Yeah.
Cool.
Doing projects. So that stayed on. Then I went to where Nora is in Chicago. Yeah, that's the story.
Nice. And so how did you get into studying cosmology?
Just general interest, I think. Just trying to figure out interesting things to do, I guess. Yeah, keeping busy.
Nice.
Yeah.
And is there a specific area in cosmology that you focus in?
I've done quite a bit, varied in topics over the years. So so when I was in Chicago, there was a lot of theoretical cosmology. So it was good to do a lot of theory cosmology back then. Went somewhere else and made connections with experimentalists and then do help out, figure out interesting experiment things to do. So yeah.
Sweet.
I know, yeah.
Right on.
Yeah.
Well, I know you've got some slides with some cool pictures that you want to share with us, and tell us a little about what we can expect in the post James Webb Space Telescope world. I'm excited that we're already talking that way, even though James Webb probably got a 20-year lifespan once things get operational this summer. But yeah, tell us a little bit about what we might expect after James Webb.
Yeah, so, James Webb, if you think about it, right, they started talking about it back in 1996, and they launched it just a month ago, 1.5 months ago, whatever, right? So 25 years. Yeah, so we say, yeah, James Well will operate for 20 plus years. Then you can't wait till 20 plus years to say we want to launch something, because we know that it's going to take 25 years to build it. So, so we need to start the process now to have something ready. And we don't even think we can get it ready by 2040. It's going to be looking like 2045. So, you know, there's probably going to be some gap, but yeah, that's fine. But that, yeah, so that's the idea. So it's thinking process. And I don't know if somebody talked about it, but, you know, there's all these ideas in the community, right? Like, you know, lots of people have lots of great ideas. So how do you figure out like which ones to spend money on? Because the pot of money is finite. And then, so we have this process every 10 years. It's called the decadal survey in astronomy. And, you know, people set up big committees and you write your ideas in, you spend time developing these ideas, you know, so, and they will tell you, you know, what they think is interesting to like agencies to fund and stuff like that. So yeah, so we just finished one of those things just now, 2020, decadal process. It's great. I mean, they managed to work through COVID shutdown and everything. It's amazing how the community came together. So yeah, so they prioritize certain things, and in their plans, you know, they're thinking about, you know, starting perhaps what's called a great sort of a reboot of the great observatory concept. So back in 1990s, you know, they started with this Compton Gamma Ray Observatory. That was the first thing they launched. And then they had Hubble, Spitzer, Chandra, you know, quite a bit of, you know, covering the broad range of wavelengths in the electromagnetic spectrum. Wavelength, you know, you want to be out in space, outside the atmosphere. So yeah, so they're thinking about rebooting something like a great observatory concept to like have like multiple observatories covering broad ranges in the spectrum, so we can you know, study the universe. Yeah, so there's an idea in there on those slides on the right side. There's an Origin Space Telescope. It's a you know, it's a 5.9 meter. Be happy to talk about it, but the one on the left is more, you know, so that the one on the right, Origins, maybe look a bit far out. You might say like, you know, it's like James Webb at early stages. So you need to spend more time. But the one on the left is being put together right now. Hardware exists in various forms. And that's going to be launched in a couple of years. And that's, so NASA has a program that launches like smaller satellites or smaller telescopes that do not cost like, you know, many billions of dollars. Like, you know, I mean, James Webb is 10 billion plus, and, you know, but they have a program called sort of like a, you know, exploration program or explorer program, where the cap is like 300 million. So, so I think the SphereX looking at is a small 20 centimeter telescope that we want to launch, you know, that NASA is funding to launch in about 2.5 years, summer of 2024. Maybe it'll get delayed a little bit because of the COVID stuff, but yeah, not too much.
What are the goals of that telescope?
So yeah, so I think I have slides later on, but so yeah, Origin, sorry, SphereX, the smaller telescope is trying to cover the whole sky. So you want to cover the whole sky, map out the whole sky in 112 channels, so 112 narrow bands, or 112 filters, or whatever you want to think about it. Yeah, so you have a sort of a cartoon. Yeah, it's a cutaway of what the things looks like. I heard you guys were talking about Kevlar and stuff like that, but this there's a thing called a photon shield, or a, you know, sunshade or something that we call it. It's made out of Kapton. That's also a DuPont product, I think. This yeah, so it's a small 20 centimeter telescope, because that's what, you know, we can put together for that sort of, you know, spacecraft bus and telescope. But it's a gigantic, the focal plane is a gigantic field of view. So it's about almost 33 square degrees.
Whoa.
So the way I think it's like a moon or sun, like a half a degree on the sky.
Yeah.
So yeah, so you can ask like how many how many moons can fit into this area. It's a lot.
Yeah, you said 33 degrees, right? So 66 full moons.
Yeah, something like that. It's,
Wow, that's a huge chunk of the sky.
Yeah, instantaneous field of view.
Wow.
That we cover. So yeah, these are what I call Mercator areas. So they work in the infrared optical, 2000 by 2000 pixels in each. There's 6 of these.
And what will the telescope be looking for?
Yeah, so maybe, so 112 channels. So mapping the sky. So it's like a blank survey or blind survey over the whole sky. It takes 6 months to survey with the sky once. And the survey is done by, just moving the spacecraft. So we rotate the spacecraft in the orbit, just traveling along some sort of a great arc. And then Earth is going around the sun. So, we get the sort of the longitudinal coverage, on the other direction that maps out the sky.
What sort of orbit is this going to be in?
It's a polar orbit. So it's like, just in the sort of a day-night sort of a shadow, but on the night side, just a little bit by like 8 degrees kind of thing.
Will it be like a really high altitude orbit?
Yeah, it's not that high. I think it's like 600 to 700 kilometers. I can interject slightly different things, but I don't know how much you guys know about astrophotography and all that stuff from the ground. This, the satellites, this Starlink, right?
Everybody knows Starlink.
Yeah, doing lots, issues with ground photography. Yeah, even at 700 kilometers, they don't disappear. We are worrying about them right now.
I was just thinking that this sounds very similar to the TESS setup, and so I was just curious because I think they're on a very high altitude orbit. So I was curious if this is somewhat similar concept in operations to TESS. Do you know anything?
So TESS, I think, is like a Earth trailing orbit. They're much farther out, I think.
So this is going to be more of like a traditional polar orbit.
Yeah, it's a traditional, like a low Earth orbit. It's not quite low, but I think most of the Starlink is like 200, 300 kilometers or something. But yeah, we want to get to 600, 700, I think. That's the idea. Maybe next slide. I don't know. I can't remember what I had. I think there's a slide here that explains how do we do 112 filters. I think I should explain that. That's a lot of astrophotography, like, you guys, yeah, if you click that once, it'll do like a quick animation or something. When you buy off like filters, right? Like, you can buy like, like H alpha and oxygen 3 and all that stuff, right? And you take an image with a filter, like a, standard setup in astronomy is to like, the whole detector or the chip would be covered on top with a single filter, right? Like you get a H alpha image of a galaxy or like oxygen 3 image of a galaxy and things like that. Here, we have a detector underneath this, but the filter is changing across in wavelength. So like, it's like, we divide this 2000 pixels into like 14 or 15, it varies depending on the channel or the detector, but roughly like just say 20, like vertical columns, and each column is a narrow band filter. So and they're like, so here is kind of, you can see from purple to blue, there's a big jump, but right next to purple, there's another filter that, that's basically adjacent to that with the same width. So that's how we put together 112 filters on top of 6 detectors in the focal plane behind this telescope. So this is called a linear variable filter, LVF. This is sort of a new concept in astronomy, perhaps. So it's linear means like when you go from like left to right, the wavelength is changing like linearly. So let's go maybe one more slide. And I can explain perhaps how we're gonna be mapping the sky with this 112 channels. So yeah, so we had to step through, like say we are looking at like some part of the sky. So this is just like, we don't point at a galaxy, right? The spacecraft will randomly point somewhere. But this what I'm saying is valid everywhere. We just have to like move across that galaxy in small steps. So each small step corresponds to the width of one of our narrow filters. So the spacecraft bus, like, it'll give us this ability to like move horizontally on the sky by this small number of steps. And then, we come back and keep on doing this over and over again. So image we'll make on the sky is not typical astronomical images that maybe we are used to, right? A typical astronomical image would be like a B band image or a R band image or like a H alpha image or something. But here, like an image is like that middle column. That galaxy we are looking at, it shows up across, horizontally in many different wavelengths. So we had to do like post-processing the data, right? We had to take all of these raw frames and like extract out these columns corresponding to each wavelength, and then we can stack up and produce, like, by combining them, individual images of that galaxy or that part of the sky. And we can make 112 images because we have 112 channels. And then we can, 112 channels means, we can, in this visible to infrared to out to 5 micron. We can plot every spectrum in this, so every 6 arcsecond pixel, so our pixels are 6 arcseconds. So every 6 arcsecond over the whole sky, we'll have this 112 data points that we will collect in 2 years. That's the idea.
You must have to be able to point very precisely, huh? If you to be able to like make sure you're covering everything and reconstruct it, or is it more in software? I don't know. It seems.
Yeah. So there's a requirement on the spacecraft. So there's a company industry like a Ball Aerospace is building that spacecraft, and so they have a requirement that they need to meet up for this step. But then, but even if you're not exactly precise where we point, we can have small offsets. That's fine. Mm-hmm. We can reconstruct, we know where the bright stars and all that stuff, so we can always reconstruct in post-processing.
Okay, yeah.
And also our columns, like you can see, like each narrowband column is pretty wide.
Okay.
These spacecraft buses are able to point better than a 2 arcseconds, so even better than 1 arcsecond. So it's not pointing we worry about. We worry about like what's called jitter, which is like once once they point somewhere, how well they can stay on that place. Mm-hmm. As they, as the spacecraft is moving across, it's moving in the orbit, right? It's constant in motion. We are not stopping the spacecraft. So, so we worry about like, jitter, like vibrational things and stuff like that. But yeah, but they say it's pretty good. They have momentum wheels to balance and all that stuff. So.
Cool.
Yeah, but there's definitely like a new complexity and new, like, new challenges in data processing. It's a huge data set. You can imagine how many pixels over the whole sky, right? Even if it is 6 arcsecond. Yeah, and also like extracting things out of it, because it's, so by the way, the 6 arcsecond is not like super duper high resolution, by the way, right? Like, on ground-based astronomy, like SEEN is maybe like, you can get like half arcsecond kind of stuff, right? So we had to do a trade, like we had to like, we had to do like, go slightly larger pixels to be able to cover the whole sky, or like stay smaller pixels and not, not get the whole sky, right? So, but we wanted to get the whole sky, and we were willing to go with larger pixels to make that happen.
Yeah.
Neat. So yeah, so maybe one more slide. And I think that has like expectation of what we're going to be finding, right? It's like billions of galaxies. And when you have 112 spectral points, right, you can measure, like, it's not like, so in astronomy, we call them photometric rashes, but these are not photometric rashes, but these are also not super accurate spectroscopic rashes, but these are like, somewhere in between. It's a new place. But we can get distances or ratios to like lots of large things. And, there's all sorts of kind of ideas, right? We are getting the whole sky, so it's not just extragalactic stuff. It's also in our galaxy, like, we will see like, I don't know, we will get spectra for like many stars. It turned out like getting spectra for many stars are kind of interesting because that helps people studying like exoplanets to figure out like the mass of the stars. Like, people are interested in measuring masses, but something they don't know very well is the mass of the parent star. So they say, oh, the spectra would be nice to work out what the masses of the parent stars would be, things like that. Yeah, so that's the idea behind all of this. And then we are making this as a community service in the sense like NASA is funding us to do the survey with the idea that as soon as we get the data, we make them, so we will process them. And, that means like, what I was saying, like subdivide, like, and combine into like individual 112 channel maps in every frame, every part of the sky. And we will, put them within weeks, like within 2 weeks of data acquiring to the public domain. So all of these things that I'm showing here, like, it's not like us going to be finding them. We want people to be going and looking for them. So lots of people are thinking about like different projects to do. Lots of people are also thinking about like how to get like, citizen science going, like, how you're going to like, you have to mine this data set. People are thinking about machine learning, like deep learning, like, how do you mine this data set to like look for interesting things? You have computers do it, or how like, people classify things or shift through them. Yeah, that's all sorts of interesting stuff you can do with it.
Yeah, I imagine if you have a billion galaxies, it's going to be hard to get human eyes on all of those. This seems like a huge data management challenge. Do you know like how big this database is going to be?
Yeah, I can't remember off the top of my head. It's huge. It's a substantially large data set. So we have there's a center at it's called IPAC at Caltech that specializes in astronomical data sets for the infrared. So they are, substantial amount of money of the project is for that, for collecting, processing, and servicing the community through like specialized database servers and things like that.
Yeah, wow, that's really cool.
Yeah. So anyway, so the hope is we will have this and people find interesting things they can follow up with James Webb, right? So James Webb will be there. Lots of opportunity for people to study.
I couldn't help but thinking about some of the similar like conceptual designs of what you're hoping to produce with this telescope and what the Vera Rubin telescope is going to do in the Southern Hemisphere. And Lauren knows a lot more about that than I do, but I love the idea of how this trend of like creating these like vast public data sets is starting to catch on, and mapping the entire sky with different wavelengths. It's it's cool stuff.
Yeah, definitely. Yeah, Rubin telescope will, probably produce substantially more data set because there's, there's a temporal coverage over and over again. We are only doing 4 passes over the whole sky, but
they have a slightly bigger telescope.
They have a bigger telescope, and they can go faster.
Longer mission. But we're not doing 112 channels. Like that's what is super cool about this too for me, is just that the resolution and the wavelength is so neat, and that be beneficial for the type of survey that we're doing, where it's just the 6 bands, right? So being able to pair those two together is going to be really powerful.
Yeah. There's interesting sort of like, what do you do with like billion galaxies, where so remember, it's not just picking up billion galaxies in a map, right? It's billion galaxies, perhaps not billion, let's just say 100 million, maybe something like that. Even though we'll see billion, we will precisely get 3D locations for like 100 million, right? So there'll be a 3D map of like 100 million galaxies spread over the whole sky. What do you do with it, right? So like what kind of things you can do? So it turns out there are interesting cosmology things. You can ask interesting cosmology questions like, what were the initial conditions like produce these galaxies and stuff like that. So something that cosmologists are interested in is understanding this early epoch. It's called cosmic inflation. So I know Nick with his CMB experiments are trying to get a handle on that with this B mode polarization and stuff like that. But there's a different way it turned out you can answer that, not studying the early universe, but studying galaxies today. It turned out you can also answer questions about inflation on the initial conditions, like what, on the process that laid down the seeds that made these galaxies. Was it Gaussian distributed or was it non-Gaussian distributed? Like we're going to be asking, like, is the 3D distribution has some sort of a departure from like a, like a Gaussian distributed set of galaxies on the sky and stuff like that.
I bet you can also make some really cool posters.
Yeah, probably. We'll see. And there's people. So yeah, I should say, like, there's another group interested in like. So we are taking essentially spectra, and then I should say that some of these channels have like high spectral resolution between 3 to 5 microns. And some of these sight lines in our galaxy passes through like star forming or planet forming clouds and planet forming disks. And in the 3 to 5 microns, there are signatures of like water and like carbon dioxide, carbon monoxide and stuff like that, spectral signatures. So yeah, so then the idea is to take a cosmic census of like, life forming material or, organics in planet forming regions or star forming regions and stuff like that. We'll be able to do that for the first time. That's exciting. Yeah. Anyway, and I should, yeah, so like I guess James Webb takes 25 years and all of that. Even this small scale project, we started talking about this in 2012. That's the initial time scale we started talking. So you can imagine, right? If you launch in 2024, even that, so it's like, like way 25 times cheaper than James Webb. I don't know how many, yeah. It still takes like 12 years to get one of these things, together.
So half a career instead of a whole career.
Yeah, pretty much.
It's pretty cool when you think about it, where you can work on one project, for the most part. I mean, obviously you did other things, but
right. Yeah. And we are hoping, like, it's funded by NASA right now for like all the other things NASA does, like tests and everything else too. They initially fund you for like 2 years of science operations or mission operations, what they tell you. And if they think it's really going well, and if we get other people to say, oh, this is going great, and we should keep doing this or doing something else, whatever, with that same, telescope in the space, they're more likely to keep running it. We don't have like things that's going to break down in 2 years. So we don't have like, helium coolant or whatever that's going to be, disappearing after 2 years. So we can probably operate this for like, I don't know, 8-9 years.
Is it just passively cooled?
It's passively cooled, yeah.
From the little cone thing?
Yeah, that's that star-shaped cone thing.
It makes me think of the things that dogs wear. The cone of shame.
Yeah. So yeah, so we'll see how far we can go with this stuff.
Should I take it that the part of the project you're most excited about is the cosmological implications?
Yeah, things like that. I'm also interested in, like, so I didn't talk about this, but when we do the whole sky, if you think about it, perhaps like, it's a polar orbit. So every orbit, it looks up in the northern pole, every orbit, and every orbit, and we can also look at the southern pole, right? Whereas, in the longitudinal, like in the equator, we'll be all over the place. So so every orbit, so orbit is about, I don't know, 90 minutes or something. We can get like, 6 minutes of data of the northern hemisphere, like a north pole that cap like 33 square degrees or whatever we're talking about. And same thing in the south. And every orbit, so that you can co-add those data. It'll be the deepest data from this survey, because there'll be so much data staring at like one part of the sky. So yeah, so we have a project going on, which is to like use that deepest data to look for like signatures of like highest redshift galaxies, like evidence for like, the earliest galaxies, like, you're just like deep drilling, right? by naturally, like, we are not deep drilling by design. I mean, it's the way we set the orbit.
Yeah, just to check that I've got this right. So as the Earth's going around, it's doing a polar orbit around the
Yeah.
Earth and constantly, I guess, side facing to the sun. So
Right.
it never actually looks at the sun. It never looks at the sun and it never looks at Earth. It's always looking away from Earth and perpendicular to the sun.
Pretty much. Yeah.
So yeah, you get those two spots really well. Cool.
Yeah, and it's sizable. I mean, because our focal plane is large, but we still have to shift. So it's funny, like when you make this deep drill field, the center is covered in 112 channels, but you can imagine there's like a there's like a half circle or whatever, or like an annular region, which is like only covered by like your outer channels or something like that, right? Like it's not covered by all 112 channels because we are not shifting all the way. Yeah, but still, lots of data, lots of area, lots of things to play with.
I guess this is, I guess, imagining the solar system and the galaxy, those two spots would also be looking out of the galactic plane. So you don't have as much of the galaxy in the way.
So they are the ecliptic poles, right? So it's in the ecliptic plane, they are the poles. So the galactic plane is slightly at an angle.
Yeah,
But yeah, they are still out of the galactic plane,
Mostly,
but it's not galactic poles.
Right.
Yeah, so can't wait to share all this data with everybody and get everybody excited to write things or do things with it, because there's so much. And as I said, we are doing mostly a community service, community product.
Very cool. Asante, thank you so much for sharing.
Yeah,
this.
thanks for
I'm excited to see this
having
thing launch. Yeah, can't wait to see the data as well. Any last thoughts you want to leave us with?
No, that's great.
Wonderful. Well, thank you so much for your time. We really appreciate it. We've got a thank you gift for you, and Maggie, our operations director, will reach out to you to get you that gift. So yeah, thanks again for being here.
Thanks.
Thanks to the co-stars for being here. All the folks behind the scenes, Gavin, our stream master, Maggie, operations director, Wyoming Stargazing board of directors, and everybody else who makes the Cosmos Show possible, especially you out there who are watching. Thanks so much for being here, and we'll see you again in a couple weeks. Until then, be well, and don't forget to look up. We'll see you next time. Bye.
Bye.